lying just south of the Marysvale Volcanic Field, the Sevier River winds its way north through the landscape as a living testament to Utah's rich geologic history. Throughout its journey, it whispers ancient tales of once molten rock and powerful volcanic outbursts. Each spring, the rush of melting snow waters carries fresh nutrients from the surrounding mountains to renew the entire Sevier River Valley, bringing a new layer of premium topsoil to the farms in Delta, Utah. This video is the story of that journey.
Hi everybody, Stuart from Liquid Dry. We're up here today in the mountains of Utah, just south of Richfield in the Marysvale Volcanic area. We're here to kind of talk about where our water comes from, where all the minerals in our valley come from. And we're here today with Keith. Keith's a geologist, and Keith, why don't you tell us a little bit about your background and what.
Well, I'm a 20-year geologist. I got both of my degrees from the University of Texas at El Paso. And actually my background in school happened to be volcanic, igneous, and metamorphic rocks. I've been working in the oil field for the last 16 years, but I'm always happy to get an opportunity to get out into nature and come back to my roots, which are volcanic rocks, and get a little bit of break from the drilling sandstones and carbonates down in Oklahoma and West Texas.
So is this your detox trip?
This is the detox trip, you know, talking about the good minerals that we can get in our grasses and nutrients in our supplements. There's a reason that we came to this particular spot, and this is the birthplace of the waters and the soil that we have in Delta, Utah. And we wanted to come into the kind of the heart of this volcanic complex where it all started, not only to get the beautiful scenery, but to talk about the processes that work the rocks and break them up and transport them down along the river valleys, out of the mountains, into the Sevier River Valley, and ultimately to the Delta at Delta, Utah.
Right. So we've been kind of bouncing around the mountains a little bit today, or you've taken us, we've looked at some different types of rocks and some of the different activity from the volcano events, I guess is multiple events.
Yes.
That kind of led up, that has built this battery of minerals that we pull from every time it rains and snows and
Yes.
freezes up here.
We wanted to get up in here and take a look at the different types of volcanic rocks that are more prone for the minerals like potassium, magnesium, calcium, a little bit of iron, and get up to the source where they're originally kind of falling out of the mountain and working their way down to us. One of our shots up in the valley, you could actually see a direct line to the Marysvale Volcanic Field, so it makes sense that its eruptive rocks would end up where we are.
And that's that peak right behind us over here?
Yes, it is. And in fact, it's that entire mountain range. There were 5 distinct calderas that took place, and that is the Marysvale Volcanic Field. And this is a really good spot to come because the eruptive components of that volcano have ended up all the way over here in this mountain and in this valley where we are right now. This right here is an example showing different events that have taken place in the Marysvale, and you can see the lowest unit is a mud flow. It's a very brecciated rock with lots of lithic fragments in it that came rushing off of the mountain as a mudslide, a big mud flow. And then the next layer up on top of it is a very light ash layer, not welded, it's got full pumice in it. And then the layer on top is an ignimbrite or a welded tuff. And this would be an example, just so you know, this is an example of a non-welded tuff. You can see the bits of pumice in here. They're not squished down, they're not laying down. And it's kind of loose and airy. It's got the little vesicles in it. You know, that's one of your feldspars though, bud.
Oh, right there.
Right there.
And that's where the potassium comes
This
from?
is correct. So this light-colored rock right here is a potassium feldspar in a tufaceous igneous rock. So this was bits of rock that were blown up into the sky as these little individual particles. They shot up into the sky and ultimately rained down right here as the ash settled out of the clouds. You know, you have to think about the amount of energy that it took to get these particles all the way up into the atmosphere and all the way over here.
Yeah, wow.
Right? So it's these little bits that are weathering out and working their way into the valley. And this is just a really neat piece. You can see the amphibole, you can see so these would be your longer chain silicates, you've got the feldspars, and then you've got some quartz. You've got it all in an ash. This is a perfect example of the rock that's feeding into Delta, Utah.
Wow.
Every single one of these little grains breaks up and ends up where you live.
Wow.
And so the potassium is in these light-colored feldspars. And shoot, this is the rock. This is exactly what we wanted to find.
So over the course of eons of time, nature, ice, water, erosion just kind of breaks this down and refines it?
Yeah, exactly. The potassium feldspars have a very, very pink color to them. And that pink color is kind of the overtone in these rock units that we can see behind us. And so I wanted to make the point that these are potassium source rocks that we can see in the distance here. Beautiful outcrop though. That's textbook stratigraphy for a volcano. That mud flow came down the mountain, and the ash that was shot in the atmosphere eventually fell down on top of that mud flow, and we can see it right here. And I think that upper unit is gonna be a separate event. But the two bottom ones, the mud flow and that ashfall tuff, are part of the same eruptive cycle. In general, the lighter colored igneous rocks, more what we call felsic in composition, higher in quartz and potassium feldspar, are going to be more explosive in general. They have higher gas, and you have longer silicates. So some of these black minerals in here that are kind of longer.
Oh yeah.
Those are longer, and they make the magma more sticky and less flowable. This dark rock has just short silica tetrahedron and some other stuff, and it's able to flow. It's very loose, it's very liquidy. This is like rock candy with gas in it. And it's just, once the pressure is released, all that gas has to go somewhere at once, and it just blows the rock to bits.
Okay, wow.
The gas isn't able to flow through the liquid very easily.
Okay.
It's kind of trapped in the liquid, and once it flashes, it goes. And you end up with these pulverizing, destructive, eruptive events. The lighter volcanic rocks that we see in the area are going to be the source of your potassium. Okay. And that is in the potassium feldspars that we see here. And these are more felsic, light-colored, explosive igneous rocks. Okay. So as compared to the darker, more flowy, less viscous magnesium calcium bearing rocks.
Okay.
And see, here's this is a vesicular basalt here. This is going to be your magnesium rock. You see this? How it's got these vesicles? Those are gas bubbles. And this was definitely a basalt flow. Okay? This was not erupted into the sky and fell down as ash. This flowed out of a cinder, out of a cone of some sort.
Okay.
Or out of a hole in the ground, and came out as liquid hot magma and flowed away from the eruptive center. So this is going to be more of your magnesium source. The more mafic, the darker, the more basaltic the rock is, the more tendency it's going to have to carry magnesium in it. This will also, and I just want to be clear that this will also carry a little more calcium in it as well.
Oh.
The magnesium and calcium kind of come together. Uh-huh. Magnesium and calcium, they're both a 2+ cation. The calcium is actually bigger, a bigger atom, so it actually doesn't fit as easily into the crystal lattices, and in some cases magnesium goes in first, but the calcium and magnesium come together in the igneous rocks.
You mentioned something about the color that we're seeing on this rock here.
Yep.
It's coming from another mineral.
It is. So anytime you see kind of a rust or a darker color on these rocks, what you're seeing is the rusting of iron. These rocks actually contain quite a bit of iron, and that is another element that's working its way down to Delta, most certainly.
Wow.
And really, like California, Italy, some of these places that have a rich tradition, or at least, you know, common parlance, these are the places that, you know, grow great crops. They're all volcanic soils just like this. It's the same thing. California, Italy, and here in Utah, we have the volcanic ingredients to make top tier soils. And one of the things that's the strongest breaker of rocks up here is the ice. So in the wintertime, when we have the rain and the snow, the water gets down into the cracks of the rocks, and when that freezes, that breaks the rocks apart. So these rocks, it's just really important. We can see the outcrop here. Look at every single crack. Every time it rains and it freezes, ice forms in those cracks and pushes it apart just a little bit more. It might be very minute, but over the eons of time, that's going to happen every winter multiple times, and you start to break it up. And as if you look up, you can see the bigger rocks are closer to where they fell out from.
Yeah.
And as we work down, we can see the rock size kind of getting smaller and smaller. This is a microcosm of the processes that take place geologically over time and break these rocks up into the smaller component pieces and eventually into the chemical elements in the water and the soils that get that are uptake by the plants and eventually ingested by us.
Yeah.
So it's very interesting. You can see the particle size getting smaller and smaller as we get down into the drainage basin, and as we get out there, it's going to get smaller. In front of the mountain range, you're going to have bigger cobbles, you're going to have bigger rocks. But the further into the valley you get, the smaller and smaller the particle size gets.
This is snow melt that's coming off the mountain right now.
Yep.
And
it's carrying the sediment that it was created up at the top, and it's carrying it downriver.
grinding up the rocks, breaking those little bits and pieces apart, refining it?
Yes, that's exactly what it's doing. We are in Earth's machine. We're at the orchard where the nutrients are created, and the Earth's machine is water, gravity, and the transport and moving of these minerals down into the low spots.
So it's not just a little patch of minerals that it's going through. This whole mountain complex is a mountain of minerals.
Exactly.
That this river is traveling.
Exactly.
Continually picking up and getting saturated really with.
Exactly.
Yeah.
We have an almost unlimited source of the minerals here in this valley, and annually, daily, anytime it rains, that water all from these mountains, from these cliffs here, all ends up right here in this river and ultimately in Delta, Utah.
Wow.
When I look at this, I just think of the power, gravity, the energy of this water, it's just really magnificent. And again, to think that this sand grain from right here is gonna ultimately end up in Delta is really an incredible thing to think about. And the sediment that ultimately makes it down to Delta is the most refined and kind of clean, well-rounded sediment out of the whole bunch. So it makes good soils for drainage. You've got the chemical elements that have the nutrients for the plants themselves and ultimately for us.
Right now we're just outside Marysville in the Marysvale Volcanic Field, kind of in the heart of the caldera, you said?
Yep.
So we're right in this volcano, standing next to the Sevier River, which is the river that feeds the water down into the Delta Valley. And we're surrounded by these potassium-rich deposits right here, right?
Exactly, that's exactly right. This is mostly glass and pumice and rock fragments from the volcano, and the rock that the magma was sitting in got scraped up and blown out with the rest of this stuff, pulverized and beat up. And we're looking at the ash bed from the big cloud that came out and settled down right next to where it erupted.
Wow.
And this ash has potassium feldspar in it, i.e. potassium source, and the glass, which is very easily dissolved by water, is also chock full of potassium. So we're looking at a really good source for potassium and other minerals. Silica is a big component. You're gonna have some calcium, a little bit of iron, but it's all kind of contained in these ash, which is really your primary erosional source. It's the quickest source to these minerals that are making it down to the Delta Valley. The actual deposition of these rocks would have been in the 500 million year old range. These are actually going to have some of your calcium and dolomite in them, but these rocks were transported off of the west coast of North America at the time, thrust up onto North America essentially, and were mangled and folded and faulted and thrust up to where they are now. And later, in more recent times, kind of around the time of the Marysvale Volcanic Field, we start to have normal faults, which are kind of basin and range, where you have one side drop down relative to the other. And that's what's exposed all of this in this mountain range.
Wow.
So
this really is an intersection of all these events.
Absolutely.
You know, wow.
Absolutely. A long geologic story has been told here, but these are 500 plus or minus million year old rocks that were moved along a 300 million year old fault, then buried until 20 million years ago when Marysvale erupted. And around the same time, you start to get the basin and range, or the extension of the North American continent, and these big cores of ancient thrust faulted rocks being uplifted and exposed at the surface.
Wow.
And also happens to form a nice bend in the road for the river to have to go around. So,
which literally, I mean, we're within a couple of feet of the river right here, right? So not only do you have all of this volcanic contribution, but just the deposited contribution that exists here, continuing to add to and contribute to the...
Yes, sir, that's absolutely right. You got a lot of plant fuel in these rocks as well. I think the volcanoes play a very significant role, but you cannot discount the contribution that these ancient Paleozoic rocks have made.
Wow. So the river's talking a little bit differently to us here than
Yep.
we are when we were up farther in the mountains. It's really slowing down.
Yep.
It's pretty calm right here.
And it's starting to dump out the sediment that it was carrying with those high velocities that we saw down by Marysvale.
Yeah.
Now the river is slower, subdued. It does carry a heavy sediment load, but it's taking this all the way down into the current day reservoirs, but back in history would have taken this down to Delta. And as you can see, this is just the lazy river now.
Wow.
And just to our left is where it turns south and heads down towards Delta.
Keith, last couple of days we've been kind of traveling around up in the mountains, and we were up at Brigham Peak.
Yep.
And in the Pine Creek area there, and up above Marysville.
Beautiful.
Down into the Sevier River, and just kind of following the water where it comes out into our valley here in Delta. This is the ancient seabed, old, what we now know as the Great Salt Lake, but back in, referred to as the ancient part of the lake was Lake Bonneville.
Mm-hmm. Exactly.
Right. And it's interesting. When I think of a volcano, I always think of just, kind of that magma kind of rock,
mm-hmm.
the lava that,
like a hard rock.
Yeah, but you've taught so much about how much more there is that's coming out of the volcano, and just kind of that process of all those minerals. I mean, there's a whole recipe of minerals here.
Yep.
that come down. It's just been an amazing adventure.
It really has, and what it does is it shows how volcanoes are really the source of everything that we have on this planet. The sedimentary rock started as a volcano that's been eroded and worked down, and so we can see the elements that are contained within the earth are being erupted out through these volcanoes, and erosion, weathering, and gravity essentially take that and redistribute it across the entire world. And we're basically the result of stardust having volcanoes blow the rest of the elements out and make them usable for the rest of us.
Wow. And sort of our delta, and you can kind of see, like, as you get down into the valley there, just really kind of how flat it was. It's just very calm lake bed.
Exactly.
Right?
Exactly. This was a giant inland sea during Lake Bonneville time. And we're actually sitting up on somewhat of a pediment, or some of the stuff that was shed off of the mountain, but you get very quickly down into the salt flats, which are indicative of the ancient Lake Bonneville bottom. And we'll see some more of the stuff as we continue, but it's an extremely great vista here where we can see Delta, Utah, where the actual main part of the sediment was dumped out in a fan-like shape, just like the Mississippi River Delta, like many of the deltas around the world. The river would have kind of cut through this mountain range to the north of us, come down into the valley, and when it hit the ancient lake, about where you can see the trees, and the shoreline would have changed through time, but basically where you can see the trees is where the sediment slowed down because it hit the lake water and dumped that sediment out in a giant fan shape, and that's where we have the farms today. That's the terminus of everything that we've been looking at for the last few days. All of the refining and pushing and grinding and transporting ultimately literally ended up right there. And we know it really didn't go much further than that. And so we have a really unique situation where we have a single river in a single state that travels north up along the mountain range, circles around, and ended everything right here. It's absolutely amazing. That river never went anywhere else. There was no other places to dump the sediment. That was the very tail end, and it had the best of the best with it.
Wow. So we've got all the evaporation from the lake, and just the massive deposit that left behind.
Exactly.
And the constant
recharge.
The recharge, the inflow and the recharge constantly of all these minerals, just
exactly.
Continually and continually.
And every year, and really this is the best time, just when you all are harvesting, all that snow melt, we just saw it. This is the peak. This is the kind of the fresh pulse that comes this time of year. In the past, it would have actually flooded out that whole floodplain. The river's been cut down into its sediment now, so it doesn't have the same kind of flooding that it used to do, but it certainly did that for millions of years. Yeah. And it dumped a really nice pile of sand full of elements, getting recharged with waters fresh out of the mountains every year. You can't beat it.
So Keith, you had us stop here. What were you trying to show us here?
Well, it's kind of an inconspicuous spot, but this is actually really important. Where we are is at a cut bank of the Sevier River. We've now come out of the mountains. The high energy flow has stopped. Has stopped at a place where you could see the kind of lazy river working its way down. Well, it wasn't always exactly like that. When this was first deposited, this was all deposited uniformly when the river came out of the mountains, hit the Lake Bonneville, and it had to slow down on the coastal plain. And that water came through here, deposited all of this sediment. But as Lake Bonneville started to go down and evaporate, the river had to continue to make it out to the lake. So what it started to do was cut down through the delta that it had built out in this area. And what you can see in the distance is the cut bank where the river has now cut down through all the sediment around us, on its way down to the delta and ultimately to Sevier Lake. And what's important about this is that we can actually see the profile of the soils that are down in delta that the grasses are growing on. So this is just a nice cross-sectional view of the sediment in the delta that we're going to go and see next, where the farms are located. Well, this is really cool, and really I was looking at the map view on our way in, we're kind of getting out towards the toe of the delta here, aren't we?
Yeah, really
and
are.
You can see the terracing coming down, as you work towards the sea, the landform kind of just slowly works its way down.
I never thought about that I've lived here for 12 years. I've never really thought about that as much as I did today on that drive.
Yeah.
Just as we came out of that river dip, we kind of came up high.
And you just terrace on down.
You just kind of terrace on down.
Yeah. And you're really looking at ancient lake levels. And that's how they all work. It's worked the same in West Texas where I grew up, and that's actually kind of the vibe I had coming here. This isn't too different from West Texas. There's a little bit of salt. There's some mountains in the background, and definitely more fertile than out there. But this is really neat, and I think we're here kind of towards the terminus of it, and you're just out into the ancient Lake Bonneville.
Yeah, wow.
You've got Pavant Butte here in the distance, and actually if you'd pan around there, Tommy, this is kind of important, because not only do we have a potential smaller source, more localized source, but the ash that came off of that volcano could have ended up right here, and that would have had a whole bunch of magnesium in it. And then the other point I'd like to make while we're standing here is, after all the work and all the miles we've traveled, we can still see the volcanic source of this sediment. Marysvale Volcanic Field is there. The snow, it's a little hazy today, but the snow-capped peaks in the distance is ultimately the source. On the other side of that mountain is where the Sevier River starts, and it works its way all the way north behind the ranges in the distance, cuts through the little valley right here, turns west, and then south to where we are. And again, it's just absolutely incredible that this river is all contained in one state. You don't have to fight Arizona for your water. Everything that we have, that we're standing on top of right here, started at that snow-peaked mountains. Some of it's come along the way from other sources, but it's just really incredible to think that all the water that we saw there is ultimately going to end up here.
Yeah.
Because it's important to remember that all the groundwater, we see the surface river, but all that groundwater is working its way underground through this delta system.
Yeah.
Absolutely.
Wow.
So it's really incredible. And I can't speak to how cool it is to see your potassium and mineral source with the snow peaks over there. And we know the river went back behind those mountains and around and just ends right here. This is the end.
That's it.
It's really incredible. You don't really get to see that. We kind of traveled the course of the river, and it's so localized and unique. I don't know that there's another river like that in the United States. I bet you there's some in the Himalayas and stuff that kind of have all a local system that don't make it to the ocean, but this is it's really unique.
Wow. I guess I never thought about it quite in those terms.
Yeah, it's a really unique setup. You're at the very end, final refining phase. Like, there's nowhere else for this water and sand to go.
Yeah.
This was the end.
Wow. Keith, thank you so much for coming. Shout out to Tommy. Tommy's been
he's been a good worker.
Working the camera, and actually he really kind of coordinated as a close friend putting this all together. Tommy, thank you so much. Keith came a long way from Oklahoma.
Sure.
Thanks, man.
Thanks for having me. It's worth it. It has been worth it for me.
Thanks.